Today we're talking about exponential graphs. It's a graph that's exponential that has the word exponent in there. So there's going to be an exponent somewhere, and our exponent is going to be x. So the definition of an exponential function is a function of the form y equals a to the power of x. So you see x here is the exponent. That's why it's called exponential function. The a here is a positive constant. So it can't be a negative number. It's going to be a positive number, and it's going to be a constant, meaning it's just a set number. All right, let's look at a very simple example of an exponential function. Like I said, it's y equals a to the power of x. In this case, our positive constant a is a 2, all right? Y equals 2 to the power of x. We want to draw the graph for this function. In order to draw a graph, we need axes and some graphing paper. Before we can graph it, we need to find some coordinates of points that we're going to plot. So let's do a table of values. We're going to look at these x values and find the corresponding y values. So first, let's do an easy one. Let's do 0. Y equals 2 to the power of 0. Anything to the power of 0, as you remember, is 1. So in this case, y is 1. X is 1 is also an easy one. Y equals 2 to the power of 1 equals 2. 2 to the power of 2 equal 2 times 2 is 4, right? Plug in 3 for x. 2 times 2 times 2 is actually 8. 2 times 2 times 2 times 2 is 16. Now the negative numbers were a little harder, right? Y equals 2 to the power of negative 1. That meant that it was 1 over 2 to the power of 1, which equals a half, right? Remember, we did a section on negative exponents. That's the case here. So 2 to the power of negative 2 would be 1 over 2 to the power of 2 equals 1 over 4, 1/4. And negative 3, 2 to the power of negative 3, we rewrite as 1 over 2 to the power of 3, which equals 1 over 2 times 2 is 4 times 2 is 8, 1/8. And you see the pattern here, right? It's 1, 2, 4, 8, 16. Here it's 1 over 2, 1 over 4, 1 over 8. So this one's going to be 1 over 16. Trust me. Okay, then we take these values and we draw a little graph. I've done that before I started the video because that would take forever, right? I already made my markers for 0, 1, 1, 2, 2, 4, 3, 8, and 4, 16. I just need to add the values for negative 1 was a half, negative 2 is a 4th. Oh my goodness. And here, I'm just going to draw a little mark as close to the 0, as close as I can get. If I draw a line, you have to kind of, you know, do your best. Whee! There we go. As you can see, this growth, actually, this kind of like explodes, right? First it goes up slowly, 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 and it just keeps going faster, 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 and then it shoots up, and I can't even plot the value, the y value for x equals 5, because if we look at that, x equals 5, 2 to the power of 5 is 32. I can't even, that doesn't even fit on my, that's like twice this height, right? So it just shoots up. It's exponential growth. That's because we just keep doubling the number, right? From 1 on, we just keep doubling it. So it grows very fast. Okay. Now, if they were to ask us, what would be, let's see, when is y equal to 6? That's a good question. When does y equal 6? There's no value like that in the table of values. We can estimate. So where does y equal 6? This is where y equals 6, right? So we just kind of follow this line and see where it hits our graph. And it's somewhere here. So the x value for which y equals 6 is around 2, what shall we say, it's a bit more than 2.5, 2.6. So when x is around 2.6, right? So we can use this graph to guess certain values, right? Another question that is kind of interesting, we've done gradients of straight lines. In this case, the gradient is never really the same, right? It moves up with the graph. Let's say we want to guess the slope or gradient. The slope at, let's say, at x equals 2. So what is the slope at x equals 2? That's the question. Now, x equals 2, that's here, right? And this is the corresponding y value. But what is the slope really here? We have to guess it, right? We move our ruler and try to draw a tangent. That's, remember how a tangent, yeah, how would I say this? A tangent hits it only in that one point, right? And it's, remember how it's perpendicular to, yeah, the line that hits it right in the middle. We try to draw a tangent. We have to kind of guess because, as you can see here, the tangent moves with the line and it just keeps being steeper, right? Here the slope is very high, here it's very low. We're gonna put our pen on the point where x is 2 and draw a tangent just using our judgment. Okay, so this line is a tangent to this line at this point. So the slope of this line is equal to the slope of our slanted line at this point. Okay. And how do we find slope again? We figure out the rise over run. So now I'm going to look for points where the line hits like right on a number, right on in a corner. Well, here as well, right? Here's a clear point, and then here's a clear one. Let's calculate the slope over this piece of line. We could pick any piece of this line, right? The slope is the same all along the straight line, but I tried to find points where it hits right on this, on the cross. Okay, rise over run. This is the run. This is the rise. Beautiful. Slope is rise over run. Rise over run. The rise in this case is 1, 2, 3, 4, 5, 6. 6 squares, which each square is worth 1 in this on the y-axis, so 6 over run. 1, 2, 3, 4, 5 squares, but on the x-axis every square is worth half, right? So these 5 squares are actually worth 2.5. So 6 divided by 2.5. Let's make that whole numbers, like 12 over 5, and then let's make it a mixed number. 2/5. That's our slope. And I shouldn't say equals, I should say equals about 2/5, because this tangent was just drawn with, like, you know, our best judgment. We couldn't be precise about it because we just tried to make the best looking tangent to our line at this point. Okay, so we made an estimation of the slope. Great. I just want to add one little thing about notation, because as you'll see in problems that you encounter, is that, look at our function that we just worked with, y equals 2 to the power of x. People in mathematics will also use this notation. And this is actually exactly the same. Here you would say y equals 2 to the power of x. Here you would say a function of x equals 2 to the power of x. So fx means function of x. It's a function where we enter x into it, but we could also basically say y, right? So you see these two off and on. Sometimes we use this, sometimes we just write y. Okay, and a function, I like this image of a function. A function is just a machine, right? We put x into the function, something magical happens to it, or something secret, you don't know, it's inside the box, and then there's this exit. Something comes out, and it's called y. And the function can be anything. It's a function that uses x, right? Function of x. Put x into it and we'll give you an answer. The answer will be called y, or we could call it fx. So our machine that we worked with in our example problem was x goes in, the function was, we do 2 to the power of that x, and it spits out a y value. Pretty, right? All right, see you later.